Bismillahirrahmanirrahim. Assalamualaikum. We are from Group 4 and our topic will be diabetic retinopathy DR textural pattern detection using LBP-GLCM and random forest. Our group members consist of Adam Ahmad, Muhammad FARISH HAKIMI, Muhammad AMMAR BUKHARI, Muhammad FARHAT AMNAN and I myself Muhammad SHAZANI.
Computer vision and image processing are crucial in the medical field for disease detection, particularly in early identification of diabetic retinopathy or DR, a leading cause of vision loss. This project focuses on texture-based classification of retinal images using local binary pattern or LBP and gray level co-occurrence matrix or GLCM techniques to extract textural features indicative of DR severity. These features are then normalized and classified using a random forest classifier, known for its accuracy. The goal is to develop a lightweight system that aids healthcare professionals in classifying retinal images and identifying stages of diabetic retinopathy efficiently.
Alright, this is our objective. The first one is to extract features of fundus image, and second is to classify diabetic retinopathy for 5 classes, and the third one is to evaluate the prediction result of classification and detection of the random forest classification model.
For the data collection, we have utilized a total of 1,000 high-resolution retinal fundus images to detect the diabetic retinopathy. We have obtained those images from a well-established medical service provider known as HIPEX. The following link given is the source where we can obtain all of those data sets. So the data set contains color fundus photographs with each image labeled according to diabetic retinopathy severity levels ranging from 0 to 4. All of the images were selected based on their clarity, resolution, and rich texture characteristics, making them suitable for textural pattern extraction using techniques such as LBP and GLCM.
This is our flowchart. Our flowchart will consist of load and crop image, compute LBP and GLCM features, normalize our image, and train our image, and we will predict the R stage, and lastly the output of classification that we have decided. Alright, this is our methodology. The first one is image processing. For image processing, we use optic disc-centric cropping. We will crop image by 60%, and resolution standardization, where we take image size as 512 by 512, and contrast enhancement, we will use CLAR, which is contrast limited adaptive histogram equalization, and we will convert all the RGB to grayscale. And next is multi-scale texture analysis. We will use LBP and GLCM. For the third methodology, we will use feature normalization. We will replace the missing values with median and center feature by median. We will scale by interquartile range. And number fourth methodology is optimized random forest. We use 300 decision trees with minimum leaf is 3. Feature selection is 80% out of the bag importance, and we will use node splitting. The fifth one is evaluation protocol. Our overall accuracy is 48.5 to 49%, and we have 5 classes.
Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad Farish Hakimi bin Fazri, and my ID number is 2023415024. So my task is to explain the code, and my friends AMMAR will explain the demonstration part. So let's move on it. So this is our code for load picture. First, we initialize the parameter, which is input folder. Save all the folder inside this parameter by paste the directory. Next is target size. We use this size to make sure all the images are standardized. Next is num classes equal to 5 and class name no DR, mild, moderate, severe, and proliferative DR. Next, we initialize sample per class equal to 1000, and train ratio, we use ratio of 80-20, which is 80% for train and 20% for test. Next, we use image data store function to load all images from subfolder into this parameter IMDS. The code for class distribution analysis and visualize class distribution is only about to check whether all the pictures are saved inside the parameter IMDS. And then we use function split each label into 1000 images by using the parameter we initialized earlier, and we use the same function to split it into ratio 80-20. That's all for load picture code. Next is our code for crop optic disc mascula. We make this process as a user-defined function that will crop our image. First, we make it in the loop to make sure all the image is being cropped by calling our function named preprocess image. In this function, first we check the image size. If not standardized, it will resize the image using imresize. We use the function imcrop to crop the image. First, we calculate a square crop size at 60% of the smaller dimension, mean HW times 0.6 in this code. Then we crop the image centrally using imcrop with the rectangle. W minus crop size divided by 2 for horizontal starting point in the center. H minus crop size divided by 2 for vertical starting point in the center. Crop size minus 1 is for width or height of the crop region, subtracting 1 for 0 base indexing. This crop is focusing on the retina central region containing the optic disc and macula. Next, we check if the picture is not in grayscale yet, we convert the image into grayscale. And lastly, just a simple contrast enhancements by using adapt his tag. That's all for this code. Next is our code for compute LBP and GLCM feature. First, we initialize the LBP and GLCM parameter. LBP parameter, LBP radius equal to 3, defines a 3 pixel radius for circular neighborhood. LBP point equal to 24, in the samples are pointed into 24 points around each pixel, is high resolution texture. For GLCM parameter, offsets, 12 directional offset are initialized, combines 4 main directions plus diagonals at multiple distances. Num level equal to 128, reduces grayscale intensity level from 256 to 128 for computational efficiency while preserving texture detail. LBP feature, we use extract LBP feature function to compute a histogram of boundary patterns, capturing edges, spot, and flat region. High LBP point uses to increase sensitivity to find a texture but may also capture noise. JCM feature, use gray comatrix function to generate a matrix of how often pixel pairs occur at specified offset. Next, use gray crops function to calculate 4 statistical measures: contrast for intensity variation, correlation for linear dependency between pixels, energy for uniformity, and lastly, homogeneity for local similarity. That's all for this code. Next is our code for normalize feature. The purpose of this code is to normalize the images that being extracted from LBP and GLCM earlier. We use median here for our normalization. Median is used because it robust to outliers. We add insnan function to prevent numerical instability during scaling. Next, we calculate statistic. First, for feature median, calculate median of each feature column, central tendency. Next, feature IQR, it is mean interquartile range. So we calculate IQR of each feature to spread the percentiles. Then we combine it to scale the features. We center data by subtracting the train feature with feature median. Then we scale it by dividing by feature IQR. That's all for this coding. Next is our code for train random forest model. First, we convert string labels to categorical variable for classification tasks. Next, for our task, we need to use random forest model. So the function that we use is tree beggar function. The important parameters that we pass is 300 for the trees. Large tree value assemble more stability. Mean leaf size is 3. This is to control how finely the trees can partition the feature space. And lastly, the num predictor to sample. For each split in a tree, randomly selects round square root length top features to consider for evaluation. That's all for this code. Next is the code for evaluation. First, we make prediction on test data using the train random forest model. Only use selected top feature from feature selection step above. Score inside the code contains only class probabilities. Next, we calculate the accuracy using sum. The code is accuracy equal to sum prediction equal test labels divided by numel test labels. Next, we calculate confusion matrix using confusion chart and pass the parameter test label and prediction. Next, we do the classification report at for loop part. We calculate for true positive value, false positive value, false negative value, true negative value, positive predictive value, sensitivity value, harmonic mean value, and true negative rate value. Next, we calculate macro averages. This is to treat all classes equally, critical when classes are imbalanced. Next, we do the ROC analysis. It shows ROC curve trade-off between true positive rate, sensitivity, vice versa, false positive rate, 1 minus specificity. AUC value 0.9, which means excellent, zero point 0.8 is good, and 0.7 is acceptable for medical diagnosis. The evaluation framework provides clinician with overall accuracy for quick assessment, detailed class level metrics to identify weak point, visual tool to understand model behavior, and lastly statistical rigor through AUC and normalized metrics. For your information, our model is accuracy, overall accuracy is 48.60% only. That's all for this code.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad BUKHARI bin KAMARULZAMAN, student ID 2023-670778. Here to move on to our DR classification GUI program. Now, similar to the regular DR classification, the GUI shares the same code with it, except instead of processing thousands of images, this one is made to process one image at a time. Here is the source code for the program. Here's the part of the GUI code. As you can see, and the latter part is the classification code, which uses the file from the classification.m in order to access certain functions and also the model itself. As you can see in this callback function, it loads the images from the folder and then does the classification process. Moving on to the GUI section of our diabetic retinopathy classifier. Here are the controls: insert image, reset, and predict. For our test case, let's test the severe case first. Here are the test sets. We will choose severe and we will choose this picture. We will predict. Yes, correctly classified it as severe. Next, let's try proliferative. And let's see what it will classify as. Let's use this picture. We'll predict and it has correctly classified it as proliferative DR. So that is all from me. I will pass this on to my groupmate.
Moving on to the results and discussion, we are not going to cover every single part, but I want to emphasize all these important contents. You can see on the left side of the slide, which is the classification model performance matrix. If you look at the table, we can see that class 4 has the highest precision, class 0 has the highest recall, the F1 score, the highest one, was obtained by class 4 as well, and last but not least, the area under the curve. Class 4 has the highest ROC value. Below that, you can see the efficiency matrix, where the measurement or the matrix would be training time, where our proposed model should be in between 1 to 3 minutes. The inference speed should be between 1 to 3 milliseconds per image. And lastly, the model size should be between 5 to 20 megabyte. You can see on the right side, which is the confusion matrix for our image datasets with the ratio of 80 to 80 by 20. So we have a total of 1,000 images. So there should be 800 trained images and 200 test images. If you look at the table right here, class 4 has the highest accuracy and the least accurate should be class 2, and the overall accuracy yielded is 0.485.
In conclusion, we successfully created a system to detect and classify diabetic retinopathy using image features from LBP and GLCM, then classified with a random forest model. The accuracy was 48.5%, and it worked better on the more serious DR stages, such as stage 3 and 4. A simple user interface lets users upload images and see the results clearly. Pre-processing steps like cropping and contrast adjustment helped improve the features, and in the future, Using better hardware and a larger, more balanced dataset can help improve the system's accuracy.